excited to introduce Berit Schloerke, not only because we went to school together at Purdue University, but also Berit is a software engineer at RStudio. We're always happy to have someone from RStudio come talk to us about all the exciting things that they're working on, and Berit joins us from the Shiny team. Thank you, Berit.
So I'm going to put some shiny stickers up front, so when you guys are all done for the day, we can all have fun sealing them. And then I'm going to pass these cheat sheets around. They're available online as PDFs. One is a shiny cheat sheet, and then also another one is Sparkly R cheat sheet. I won't tell you how often I was looking at the Sparkly R cheat sheet this week, but they're both very useful. And if we run out, I'm so sorry, but they are available online for free.
Does the cheat sheet tell you how to configure R Java?
No, it does not. And I wish it did. No, Sparkly R is very quick to install. We'll get to that later today. Yeah. So anyways, thank you for the warm welcome. Hi, I'm Berit Schloerke. I promise things go better than what just happened in the past 10 minutes. I'm on the Shiny team at RStudio. I've been there for about 1.5 years. And yeah, so today we're going to talk about Shiny and also a little bit of React log, which is built into Shiny. And then we're going to talk about Sparkly R and about using the large data, because I take it that's what most of you are doing, with this month with all the bio data. So do a little bit of Shiny just to make sure everyone, actually, quick question, raise of hands, how many people have used Shiny before? How many people have used Shiny for more than one project? Okay. Just trying to make sure who my audience is here on this one. How many people who have used Shiny all of a sudden didn't understand why their app stopped working? That's me for sure. Great. And then also, how many people have heard of large data or used large data? How many have implemented large data? Like implemented a project that used it? Great, now we can all do that today. So that'll be good. Okay, so Shiny. Just to recap, in case you don't already know, Shiny is an R package, makes it easy to build interactive web apps straight from R. You can host standalone apps on a web page or embed them in R Markdown documents or build dashboards. You can also extend your Shiny apps with CSS, HTML widgets, and JavaScript actions. I want to just reiterate that basically it just makes our users full stack developers. We already do the data, now we can do the web pages. And it doesn't take that many lines of code, which is what I really like. We hide all of that magic for you. So that's awesome. Shiny.rstudio.com is the place to go for resources. We have example apps and other things. And then my favorite is the reference. And what's the latest reference? Because obviously you don't need the past ones. It's not how R works. So yeah. All right, so let's look at the hello example. It would produce an app that looks like this. And the app is made of 3 parts, pretty much 2 big parts. The UI, which is the user interface, and that determines how it looks. So for R, we usually don't worry about that. I think the biggest component of a UI is the stars for the p-value. That's about as fancy as it gets. We're usually more concerned with server logic, or if I have a value or a parameter, I insert it into my model, and then I get some output out. And that's usually what we do, is that logic, that deep statistics right there. Even if it's just addition, that's our logic. The server is how it works, and so the UI just gives it an outlet to the web page. Most of you are probably familiar with how web pages work, so that's where the connection is. The final part is just making sure that you call your UI and server together. So if you've made your UI and you've made your server, then we'll have a Shiny app which does UI and server. There's about 10 different ways I think that you can call Shiny, but this is my go-to method. All right. for this app, amazingly, I think if we condense this down, it would be about 10 lines of code each, 5 lines of code each for each part. You could probably do it in one if you have some fancy semicolons. But let's take a look at this. I'll stay down so the mic picks me up. On the left side, we have the UI. Typically, we'll just start with a fluid page, something like that. That just says, kind of lay everything out, how it happens. Don't worry about it. We'll start off with a title, and this says Hello Shiny, and you can see that in the top left part of the image there. We'll have a sidebar with the sidebar panel and the main panel. Usually in stats applications, there's like tweak your parameters and then get your model output. This happens very commonly, and so we've tried to make that a very easy setup for users to do. In this situation, there's a bin width that can be chosen, and then that will adjust the bin width for the plot in the main output area. So if we look at the server logic, all we're doing is we're going to take the old faithful waiting times, and we're going to make a histogram of it. Except the magic part comes with the sequence of here. Sequence is the min of the old faithful waiting times, the max of the old faithful waiting times, but length out is the input bins plus 1. Just to make sure there is a bin, right? That's the interactive part that closes that loop of user input, connects to the server, server does some calculations, and then we save all of this information to a dist plot, which matches with our plot output dist plot. So that's the connection from the server to the UI. So let's actually take a look at this app, just so we can see it. Perfect. So we have our UI, and then we have the server, and as I adjust the bin width, you can see the yellow lines down below re-execute to get a new plot. Yeah. Even though it's just our simple hello world, there's a lot going on, but I really enjoy just the quickness that all of a sudden we just say, oh, it's a hist plot. We know how to make those. Now you just put it inside a render plot command, and then out it comes. Oh, please feel free to ask me questions along the way if all of a sudden something's just crazy. I tend to skip over some details. I do know that. So the magic of how the input told the server, the render plot function to re-execute is done through reactive programming. This is a concept that is not really native to R because R is very much static. You give a file in, you execute it, you get your answers, that's it. There's not and wait 5 more seconds and change a parameter and rerun it. That doesn't happen. Usually you would just make a new file and re-execute it. Or you would resave your original file. Here in reactive programming, there's 3 types of reactive elements that help us, with this situation of change, propagation of change. There's sources, which is like our input bins that we are looking at. That's things that are at the beginning of your dependency trees that you're going to be creating with Shiny. And then, or in this case, input key A. We have conductors, which I think of are like middlemen. They help you calculate intermediate things that might make your overall life easier, so you don't have to repeat calculations. And then we have endpoints, and endpoints can be things like the render plot. Like a plot is not going to be something that's going to be used for another calculation, so we just have it be an endpoint. There's also other things such as observe, which we're doing for side effects. Things like maybe printing to the screen. That's not something that we're saving or we're having execute further, but we do want to see the side effect and we do want to see some reactivity happen, but we don't want to have it continue on. So it's just an observe. That's the two type of endpoints. If we were to look at this as a dependency tree, we have input key A, which goes into a conductor value, which then that value is required by both an output key B and the observe statement. So in this case, if input key A changes, val will get updated automatically, then output key B will get updated automatically, and the observe statement, which will look at the structure of the value, will also be executed. Does that make sense? Or at least seem plausible? This is the basis of every Shiny app. And I think I just got notification of an app this weekend that had, I think it was about 3,000 nodes in its dependency graph. It was very fun to take a look at that. So let's take a look at a demo of, I would say, what's more of a typical application, Shiny application. This was written by Joe Chang. He is my supervisor. In this one, our studio hosts CRAN, and he was curious as to who was downloading packages the most. In this case, he calls them whales, because people were downloading like gigabytes and gigabytes, and it was not of just like, oh, download the whole CRAN. They were like downloading dev tools every 3 seconds. I don't know why, but they were doing that. So let's run this CRAN whales here. So in this case, for today, or is it yesterday, earlier this week, we're showing the top 6 downloaders, and it's currently parsing the data. So this is that sidebar. Here's the main layout. Happens a lot. We can then also hide that sidebar. So on 4/29, there was 3.8 terabytes, 3.7 million files downloaded, and 86,000 unique visitors. But the top 6 are represented in the light green here. So that represents 6 people. So let's see who they were. Mainly it was this person. For anonymization, they're the cool squirrel. Don't know where they're from. And by the hour, cool squirrel was just kind of consistent. Silly fawn just came out of nowhere, downloaded a whole bunch of stuff. And then Swift Gorilla, if we look at that one, it was downloading DevTools constantly. One package, nonstop. And it makes no sense to me because it's the same package all day. But it did it for 8 gigabytes worth, so that's really impressive. But this is a typical Shiny app. So one of the things that we can do is we can change the date. So change it to 28th. Kind of fades out a little bit. Things are recalculating. But as the coder, remember, I didn't have to say, oh, update the view. All I said was, here's a new value. All the reactivity will just solve for itself. So on Sunday, less traffic. It's only 2 terabytes, not 3.8. Still kind of a similar pattern here, and still kind of have like some people downloading. This person's probably downloading 1 package all day. So, yeah. All right, so that's CRAN whales. That's more of a typical application. All right, so now we're going to talk a little bit about Reactlog and how we can debug those applications. So if you built your Shiny application, awesome. But you want to add a new feature, also awesome. And this happens every time your reactive output does not update. You're super sad and confused. And there's no errors in the console because it executed, so it should work. So what do? We want to figure out what's going on. So debugging the reactive code in a working Shiny application is not easy, because if there's no errors, then there's nothing to follow. There's no breadcrumbs, there's no nothing. So we need to know the reactive state at all times to figure out what is it listening to, because right now we have a miscommunication that's going on. A is not talking to B, and that's our new feature. So the solution is React log. So what is React log? It's a brand new application, like literally, I think last Friday is the official tweet date of Shiny 1.3.2. That's where it was officially supported with React log. Otherwise, it was in a dev version until then. So right now on CRAN, you can download Shiny just like normal, install.packages, and if you also install React log, and so you can do this yourself. I'll show that on the next slide here. What it does is it takes a snapshot of the log or the history of all reactivity interactions of your Shiny application. So it records who's communicating with who in your Shiny app. And that way you can traverse forward and backwards throughout that log to figure out where your communication is breaking down. Because these graphs get quite large, like I had the graph earlier this week of 3,000 nodes, searching is very important, because really you don't care about the 3,000, you just care about this small little window. Maybe the ancestors or the descendants of that person that you're interested in, but usually you're just interested in a very small window. So setup. Yay! Now all we can do is we can do a install.packages with Shiny dependencies is true, and you'll get React log installed already. And then setup. Normally, we just do our Shiny run app, and that's all we would do. But if you add in options shiny.reactlog is true, then you've enabled it, and so Shiny will actually start recording all the information in the background. If you close your app, you can just say Shiny React log show. Otherwise, what I do normally is I just say Command F3. If you're on the newer Mac, make sure to hit the FN button, because it's not FN3. But that's what I would do, and it just pops up a new window. So yeah, all right, so let's look at Pythagoras theorem, right? We know the app, how it should work. It's Pythagoras, right? So A squared, B squared, add them together, and get C squared, and then we can calculate C. So, all right, so if I run my app, we have A, B, and C. And I know this is kind of like a more trivial app, but that way, we know the infrastructure already. We don't need to explain that. So we just need to know how the communication's working. So one thing I can do is I can change it to 5, and then 12. We get 13. Everything expected. So Command FN, FN3. Now we get our React log. So I'll just make this full screen here. Great. So this is the initial loading of that Shiny application, and if I hit the right arrow, you can see that the value was deleted to NA, so everything invalidates, kind of had a bad value. And then actually our text will start calculating upwards on those dependencies. And in this case, it found NA values, but then we rechanged the value to 5. So it invalidated all the way down, and then the outputs wanted to be visible, so they wanted to calculate, so they start calling all of their ancestors and recursively upwards. So this is actually the state of Shiny, and this model was not visible until last week. It is very fun to see. We'll see, in a little bit we'll see how CRAN Whales works out, where it's 8 layers deep. Question? Yeah. So here, is that what you're looking at? Yes, that's calculation time. It's milliseconds. Milliseconds. Most of the calculations that are done are 0, 1 milliseconds. You'll get into some larger things like, let's say, calculated model. It could be seconds, and so it'll be in the thousands. Usually you're trying to keep everything, to me, under a quarter-second round trip. That's where people don't get bored. Yeah, so Pythagoras. Now let's load up actually a different application to where, if I look at my files, not there. Pythagoras broken. Kind of looking through, don't see too much difference, so I'm going to kill the app and reload it. What? Oh, more set working directory. Okay, so now we have Pythagoras. So let's change it to 5, something different, and change it to 12. 123, 1. Doesn't change. This is usually the interactions that you'll have as you're building your own applications, so you don't know what's going on. This is where I would say we'll do the command fn3 and enable it. Enable the React log. So this is a little different than what was there before. Before we had, A and B kind of calculated A and B squared independently. They joined, and then they split for the outputs. Here, input A is actually updating A squared and B squared. That's a bad news there. So we could fix that one. So B is never even used at all. And then the other one that we can see is actually output C verbatim is not even listening to C in the first place. So that's also bad news. So those would be two things that we could fix just by looking at this graph.
Question before we get further along. What are different colors? Yellow, green?
Oh, sure. So you can think of when you have your code, there's about 4 states that I like to think of for your code. One is it's never even been evaluated at all. So I would say it's an invalid state at that point. There's another one, we'll say 3 actually. There's another one of calculating, like this is the one that's currently being evaluated. So that's the one in yellow, right there, kind of yellow-orange. And then, so it's trying to evaluate, and just like R, it might go, multiple layers deep. And then when it has a valid value that you can just ask for it right away, then it is green. So in this case, we'll start at the very right, and it'll start calculating, go all the way up to the left, and then it'll have the values all the way back to the right.
And
So,
then gray.
and then, yeah, gray means it's not ready to, and it needs to be calculated. So like here, A squared is being calculated, and then B squared just started calculating, and B squared just finished, C squared just finished, C, and then the output just finished. Cool. Searching. So I was alluding to that earlier. Let's actually take a look at Cranwell's and run that. So I'm rerunning Cranwell's, the same app we saw before, but I have the extra flag that React log is true. So as I click on things, it'll be recorded. Let's see here. So I'm opening up a new tab, a new plot is being displayed. I'm opening up another tab, another plot is being displayed, and here I'm changing the date. So everything gets wiped because data is the most important thing for that. Everything depends on the data being recalculated, plots updated, plots updated, plots have updated, and all the numbers have updated. So lots of things going on. All right, so let's check out that, see what it looks like. So this is the initial load. Here we ended up clicking on another plot output. Then we went to the next plot output. So output download handlers. And then download handlers per hour. Good. Then we updated the data, right? So now this input data here has been updated. So now everything downstream will be invalidated. And it takes a second. There we go. And now we can start recalculating. Now it's on the third view. So in that case, it's just looking at the whales. Which one was it? There we go, this output. Download per hour, oops. Yeah, and then we kept clicking through on the other plots so we can see what's going on. If you were just concerned about the download per hour, we can look at that, like double click on something and it will just go to the family tree of that item. Or we can do things that are like whales, anything that has the word whales in it, we can search for it, such as these three elements. Or whales, whale downloads, just that guy. Very handy when you get 3,000 nodes. Another idea is you can take input count. If I was to change the count, what all downstream dependencies would it alter? So you could do it that way, and I would find out all the plots would be updated as well. Yes, question?
You can step backwards and forwards.
Yeah, so here I've just been going forwards because that's kind of what we observed, but I can even jump back quickly just for the ones that are displayed. So you can go back and forwards in this whole recording. Yeah, so that application I think was actually really dense. It had lots of dependency layers. Normally I see apps that are like 2 or 3 layers deep, like A goes to B, print to C, call it good. That usually gets the job done. I think the most I've seen is 8 or 9 layers deep, so all the way, that's a lot of dependencies deep, but it worked. They were happy with it. Yeah. And then this is just showing the family tree. If you were to double click, all of the descendants and ancestors would be pulled together just to make a smaller graph, just like we did earlier. For all of you Shiny users that are getting a little bit more advanced, remember the Shiny outputs that are not visible are not calculated. So if it's hidden on another tab, we're not going to calculate it for you. I mean, it's efficiency, right? If it's not displayed, why think about it? That's on purpose. Also, don't keep React log on forever if you're having it run on your own server, because I'm constantly recording and keeping that in memory. You will lose the memory battle. I've seen that happen. And React log is not a performance debugger. I know it does show you the a little bit of milliseconds there, but I would prefer you use profviz. It'll show you both memory management and timing, and be explicit as to this line caused your like 10-second slowdown. As much as I believe my intuition is good, It is not. Profiz is better. Please believe me when I say that. I do remember one time at Purdue, I had a student said, by Thursday, I need to get this 3 times faster. And he was not aware of Profiz, and I'm so sorry. Don't listen to this one. He wanted it to be 3 times faster, and so I was like, oh, just load up Profiz, we'll see where it's at. And it basically, 99% of his slowdown was in 1 line of code, and he was collecting things in an inefficient way. And so we looked at it and we reformatted it to be, basically like an lapply or a vapply command, and it ended up being about 100 times faster when we were all said and done. So after about 30 minutes of work, it went from 100 seconds long to half a second, about that, when we were all done. He's like, I don't know what I'm supposed to do. I got 3 days. Like, do I sit? Do I go home and play video games? Like, I was like, don't give away the secret sauce. Just go home and play video games. It was the happiest week he had. Yeah. Okay, some future ideas. In this case, I didn't show you, but you can have multiple user sessions being recorded at the same time and view them. I would like to differentiate them. I would like to display the output of a value or a final reactive. Currently, we don't have that. Things like if you displayed a plot, maybe I could hover over it and I could show you a little image. We also have an idea of expanding and collapsing groups. Things like if I had a deduper, so like if the value 4 came in and then the value 4 was set again, it shouldn't re-notify and recalculate. So I have this like collection that dedupes. Well, really that's just like 1 node in that graph, right? So, but it's probably going to take you 3 nodes to implement it. So we want that to actually just collapse and just say, oh, this is a deduper, don't worry about how it actually works. Or this is how you render a plot, don't worry how it actually works. So we'll see, but that's the future. And then also remove items from the React log graph when they're garbage collected. I've seen some ways where people could make a graph that just constantly appended new elements, but according to memory, only like a constant 5 existed. And that's because the old ones are being garbage collected. So we should take them away from the graph if they don't exist. Or at least notify you that, hey, this was garbage collected. And then, everyone wants a super application. I want Profiz in React log in the same window. And if I hit right or left, it tells you what line of code is executing. That would be amazing. But, we have to keep pushing forward. Any questions? This is like my baby for like the last 8 months, so that's why I'm so excited about it. No? No. Once, twice? All right, awesome. Oh, yes.
Are you using R or some other language to draw that plot of the reactive one?
So R is doing all the initial recording, but it's really just a JSON array. And then to display the network graph is done with Cytoscape.js, which is a graphing library. And it's not D3 or anything like that. It's actually done with a canvas on front, but it's all JavaScript to do the graph and the interactions. Yeah.
I'm pretty interested in how to step back because most debuggers can't do
Yeah. So in implementation, I actually just redo the whole thing. If I go to -1, then I recalculate the whole thing because it's fast enough. We actually do that even going forward. If I go to the next step, I recalculate the whole network and what it should be, and then I just do a diff on remove this edge or add that node or change the color. And that's about it. So then for the implementation side, it just does a small change, similar to React.js and how they do HTML updates, if you're into that. Yes?
How often do you find some kind of circular dependencies with something like this, and how do you resolve things like that? And just thoughts on that?
So there was another React log. We'll pretend it didn't say that. It couldn't handle it. This one does. And it's actually kind of funny to see. If we get some extra time at the end, I'll see if we can make an app that does that. But in a sense, what it does, you have your input value 5, and you calculate 5 plus 4 plus 3 plus 2 plus 1, something like that, like a linear Fibonacci, right? And the graph, what it does is it comes in from 5, your input 5, you have an intermediate value, and then it depends on itself, and 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 then it finally is displayed to the screen. It's kind of fun when it invalidates, because you see the lines just collectively disappear, and then it calculates and it collectively recalculates. It's fun when it's like 50 layers recursive. It worked, so Shiny does handle that situation computation-wise, in that it's actually, there's a special context for each calculation, so they are completely independent calculations. You won't be stomping on yourself constantly. But we can talk about that more later. Any other questions? Cool. Alrighty, so SparklyR. Data sizes. So this is really important, especially when dealing with R. As much as I love R, R is small data, in that it is only in memory. But plus side, that makes it really fast, right? You're not reading it from disk, or you don't actually hear your computer heat up as it's trying to find a file. But it's very fast. Sometimes when it doesn't work, we with R, we then offload it to MySQL, right? We put it onto disk, and that can calculate things in and out from files, and it works. It's a little bit slower, obviously, because it's reading to and from disk, but it is still pretty good. Now, your capability, like from before, if it's in memory, my machine has 32 gigs. If it's now on disk, we can go up to 1 terabyte, no problem. Like, it's not even a question at that point. That's a big jump. For biodata, probably in that realm very easily. Final one is large data. And to me, my definition of large data is actually a little different. People like to say, oh, I have large data. And it's like, well, really it's just because it makes it really difficult. And I have 1 million rows in my Excel table. It's like, no, that's not large. It's just very big table. To me, large is distributed. I don't care if that's 10 megabytes and it's distributed, but it's on multiple machines. It is not on just your machine. Usually when you're working on your own machine, you don't have to worry about, hey, did my machine talk to another machine? It's not a situation that happens ever. You just read from disk. Either your computer is alive or it's dead. But when you have communication, that is not a trivial task anymore. There is a very real situation where the network goes down. The machine was unplugged because who knows? It's happened, and it will happen. So it's things that have to be accounted for. The benefit, though, is that parallel computation is awesome. It is amazing. You can have a basketball court filled with computers. They can all be so-so computers. Doesn't need to be great, but they can all do a little bit, and they all do it in parallel. That's really powerful. So the hard part now is communication. Communication between machines is very slow. It's kind of like downloading things through the internet on your computer. Once it's on your computer, you can do things very quickly. But sending it back, like uploading a file or attachment in an email, right? It's very slow. Takes seconds. So we want to keep whatever we're sending back to the main machine very small. But if all the computation time underneath is large, then we can. This is a great situation to do parallel computation. So this is where SparklyR comes in. And SparklyR is actually both a medium and a large data handler. And you guys have been talking about dplyr this week, right?
Not really.
Not really?
They must probably at least some of them should already know it, I think. These are mostly advanced users, so they're probably already familiar with that.
Sounds
I kind
good.
of assume that they use stuff like that.
How many have used dplyr before? Yes, no? Oh, awesome, great, all right, perfect. So the good news is all of your tricks with dplyr will just transfer instantly to sparklyr, because sparklyr, like dplyr, can make SQL commands, right? Spark actually can execute SQL commands. So now we have a, it's a couple hops, but it works. It's a one-to-one all the way, and then it's a one-to-one all the way back. And so since I'm already familiar with dplyr, I just need to know 2 more commands, and then now all of a sudden I know sparklyr, at least for the basics. For all you modelers, there are many natively implemented machine learning algorithms in Spark. I don't know all of them. I will just claim to point you to the website. All right, so let's do a demo where we start up a sparklyr instance, and then we plot flight data by distance. And we're going to be looking at the, I think it's the New York flight data. I can't quite remember.
2013.
It's a big flight data. Let's close this and do, let's see, yeah, New York flights. Yep. All right, so let's make sure we have Spark and Tidyverse installed. Great. And let's load dplyr and sparklyr. Let's make sure our Spark is installed. Good, mine's installed. And let's set up a connection. Even if you are resistant to program within RStudio, like I am, even though I work at the company, there's a wonderful thing of connections here, connections tab, so it can tell you what databases that it knows is currently connecting to. And I have my local, and there's nothing in there right now. But if I copy in like the iris data set and the flights data set, then this connections tab will populate with information. Just thinking about it, the flights takes a second. So if we look at the flights, we can see the the head of it, just like Tibble likes to do. Or if we open up, we can actually get a whole preview of that table right there. Now, if you've ever worked with databases, I think that in itself is worth gold, because that's very difficult to do. Okay, so now we have our data. It does exist. Things are in there. We're happy. We can validate that flights and iris works. That's how this is set up. And we can also double check to see, if we look at the flights, we can see that the departure delay, if the departure delay was 2 minutes, we don't know how many rows, but it can give us the top 10 at least in the response. In this case, there's a bunch of them in there with all the departure delay of 2 minutes. All right, so given I'm working with a Spark data set, let's do this, where we have to collect all unique tail numbers and then get the count, average distance, and average delay, and then make sure the count has at least 10 and distance is less than 2,000. So we want to make sure we don't have just random data in there, just random flights, and we also want to make sure we don't have internationals. So that'll be international flights. All right, so dplyr syntax. Collect all unique tail numbers. That's it. Group by tail num. Oh, tail num. Good. It even corrected me. Summarize by, and we'll do count equals. There's the window function n, right? Where you can get the number of records. Sometimes I would cheat and just say length of tail num. But you can do the helper method of just n. Let's do average distance, so dist equals mean of dist, and is it dist? Let's double check that. Yeah, no, that's distance. Oops, could we fix that? Distance. And also, we want delay, which equals the mean of depth delay. And yeah, that should be good. And we'll pipe it into make sure filter that count is larger than 10 and distance equals or is less than 2,000. Right? That seems fair. And then let's collect it. The only thing new is collect. Collect, usually with Spark, they delay everything until it's printed or it's collected. The reason being is that you could do a little bit of commands, you could do some more logic, you could do a little bit more commands, and there's no need to touch the database until you have all of the commands. Because maybe you might be filtering it down to 5 records in the end, and so Spark will be smart enough about that to not be processing all the data. Okay, so if we run this, and then we look at delay, great. We collected all of the rows, so it's not question mark anymore. Now it's 3,200 rows and 4 columns. We have the tail number, count, distance, and delay. Let's actually, we had some warnings. So na.rm equals true. And also let's do a filter depth delay not is .na. So make sure the departure delay is not NA. Make sure our distances and our delays are good. Let's rerun it. No warnings. Great. So now we have our data set. Hopefully there's no NAs in there. So that is actually connecting to the Spark instance on my computer. It is not done in memory. And I think that is just super powerful. You could imagine that if instead of at the beginning, I just change one line and I say, oh, master equals, I just change it to some, Purdue instance in this case, and it would just work. You need to have IT set that up for you, or maybe your research group, but I think just being able to change one line like that is super powerful. But instead, we'll just do local. Great. So now we have delay. So now let's look at delay on distance and plot the size as count. So if we just throw in our AES, we'll do, X first, Y second, size equals count. And this gives us X is a function. Distance. Great. And because we're always curious, geom smooth. Awesome. So that originally was all stored in the Spark. We've now summarized it, got something that we can put into memory. Now it's small data, so now we just work our normal R magic, like normal. Great. Any questions on this set of code? Yes.
So that declare chamber, the only Spark part of it
is the only sparkly R direct function is collect, but these are actually all producing so if I print it, it's there, but if I actually look at it, it's all like Spark magic underneath the hood. I don't have it on me right now, but there's a command to actually look at the MySQL code that it generates, which I think is really cool. And so when you say collect, it's actually executing that set of code. Any other questions? Yeah, so most of this should be fairly familiar. Just the collect and the SC thing is the only thing that's odd. Cool. Great. So let's actually look at did I get it right? I'll just rerun it. Awesome. Okay, So now let's actually do a little bit more Spark magic. So here, let's set up our flights table. We're gonna make sure that the distance is less than 2,000. We're gonna make sure the depth delay is not NA. And then we're just gonna add in some extra characters for the month and day of that flight. That's so that Spark can understand that it's a month value and not just some number. And then we're just gonna select those 4 columns. So let's do that. If we look at it here, we can see, don't know how many rows it is, but we do have that this is what it would execute to be if I looked at the head of it. So we have departure delay, scheduled time, the month is M1, the day is day 1, and distance was 1,400 miles. Oh, yeah, here's the parameter. No, don't execute that. That's the magical select query that it's running behind the scenes. I remember when Hadley was talking about that, he was saying that we as developers shouldn't be worrying about trying to optimize our code. MySQL has done a very good job of that, so we should just make really complicated commands. It'll figure out how to do it best. So even if you start reading it, it's not too bad. It's basically just a select and then just one where statement with, a little extra parentheses. But if you had some group bys, joins, and everything, it would get quite large quickly. Cool.
I have a question.
Yeah.
So, let's see. So one obvious thing I see here is like here, so we have paste 0, and that turned into a concat somewhere in there in the SQL part. So I've always wondered exactly how many R functions like that somehow get translated to these SQL functions, and how often it is that we use some kind of R function that doesn't have a direct equivalent, and what happens in that case. Stuff like that.
I don't know. I do know that there is a translation script somewhere that says if any paste commands are ever executed, please turn them into concats. That's why when I took the mean earlier, it was like AVG, and it's like, well, that's MySQL's average, MySQL's mean function. So there is situations actually where you want to run something, let's say like a time series forecast. And I love this example because time series forecast runs C code. There's nothing you can do to replace it. So there's actually some it's kind of like a Spark apply, where it'll pull the data set into our memory, I believe, in some way, just believe that it works. It then executes the forecast function directly, and then it resaves it back to Spark. Then Spark will combine all the answers, and then it'll come back to R. That's how we try to do it with Repay at Purdue, but they now have that natively supported. That is on their website. Any other questions? Cool. All right, so let's look at trying to do one machine learning setup here. So if we take our source input and we set up that we're going to do a dplyr transform with this data frame that we just created, we then want to say, hey, look at departure delay, call it delayed, and make it a binary value splitting by the value 15. So if it's 12, it's a 0. If it's 20, it's a 1. Split it by 15. Then let's also, in R, this would be similar to cut, but we're going to make buckets. And so split this continuous value at 400, 800, 1200, 16, 2024. Every 4 hours of the day, split it up into different time components, a lot easier to solve. And call that, or from scheduled departure time, call that now hours. And then let's make an R formula of delayed, month, day, hours, and distance. And let's run a logistic regression to see if we are delayed or not. That's the whole setup. Yeah, there we go. So let's run that. Run this whole thing maybe. So flights, and let's see what's produced, pipeline. So we can take a look at this after the fact, so you can actually construct this in multiple parts. It doesn't need to be all done in one big shot. You can separate it out. You can revalidate it yourself after the fact. So now one of my favorites is we always need to do our cross validations and things of the sort. So we have our testing and training, right? So we're going to take our Spark data frame and we're going to partition it. This is the data frame that we're partitioning, and we're going to train on 10%. We're going to test on another 10%, and that leaves the remaining part to be 80%. So this is just setting up the command, it's not executing it. And now we can actually predict. So we're going to take our pipeline that we just created up above, the big complicated one, and we're going to fit our partitioned training, and then we're going to transform it with our final testing data. And this takes a second because this is actually executing it on Spark. Also nice to know, you would not get that in a console or somewhere not in our studio. So you could see the Spark job executing. And then predictions. Oops, nope, don't want to do that. Stop. There we go. Predictions. So now we can see. Great. So it's still kind of set up as there's some information in there that's now filled out, which it wasn't there before. It was just kind of blank. So now we can see how we did by doing. Did I change the names? I changed the names, didn't I? Let's see, group by applied to object of class. Let's just retry that. I sourced the whole file and killed it, so now I have to resource the whole file. Sorry. What is going on? Maybe I didn't. I'm out of my league on this one, I think. Stop it. Delayed, scheduled, distance delayed in hours. Great. And prediction. Good. So let's just that's I don't know. Weird. Alright, well, I'm going to claim that it worked yesterday. But all I would be doing here is I was going to group by the delayed and the prediction and count to see how many times I guessed a delay occurred and I was right, and how many times I guessed a delay did not occur and I was right, and the times that I was wrong. Turns out it's a really bad model in the first place, and there's not much signal. We kind of saw that in the plot. It was pretty horizontal, but it at least does decently well. We would then be able to look at the predictions, the area under the curve and the root mean squared error of those predictions. And those are pre-built from Sparkly R. So let's see if I can actually get this app to run. How are we doing on time? Yeah, I'll do this. So we could imagine that what we did is we took that model, we then just copied it over inside our server, and then now we can, and then we just hooked it up a couple times. So we have the same plot, we have the table that's working and with working code, and then we have the area under the curve and the root mean squared error. I would say it's not the best model, but it is better than 50, so that's pretty good. For min count, what we can do is we can make min count is there. Let's actually make it like 100, and let's make it for flights that are over, 400 miles, or actually from 0 to 800. There was that initial signal at the beginning, and then it flattened out. So this is actually retraining, recalculating the fit, redoing the whole thing, and setting that all up. So everything disappears. I had some intermediate times when I was scrolling, and so it's running through all of those steps right now. It'll eventually land out to be where it was. Yep, no errors. Ah, there we go. Not in Shiny, but I mean, if RStudio is connecting to it, there's got to be a way to connect it to yourself, and you could actually, there's a with progress bar, and so what I could do is just kind of like forward that progress information to the front, and so here it finished out. Yeah, so there are ways to do progress bars, but I was hoping I could just kind of copy my code, make the server really quick, and then you have an app, and 5 minutes of work, and we're running. And then if I want to change training percentage to like 7 instead of 2, it only is updating the model because the plot doesn't need to update. So that's where we get the selective updates within Shiny. I know I did a little hand wavy at the end, but is there any questions on that? Just trying to more just make this an app. Yes?
How difficult is it typically to debug your Sparkly R code when you're not in the middle of giving a talk?
Well, this last week, the demo code that they had on their website worked out really well. I'd say the most frustrating part that I've had all week was, in the last 10 minutes here. I think with the dplyr interface, it makes it really useful. If anything, what I would do first is I would take my dplyr code and I would collect maybe 100 rows, and then I would just run it with small data on my machine, get all my dplyr commands set, and then I would remove that first 100 rows and then run it on the database. There's no point in trying to debug your R code on a full data set if you're trying to do large data. I like to work with a small data set, get my commands right, and then I unleash it on the full data set. Yeah. I think the other frustrating one is I kept calling distance dist, and that's a function, and it kept telling me that I had a function for a variable name, and I was really confused because I thought it existed, but it did not. That was the only other one that I ran into. Make sure it actually exists. Cool. All right, so let's go back to Keynote. So we did that. Oh yeah, React log. Let's run this app and just open up the cool. All right, so this is actually the app that we did just now. So the important part for me is we change the count there from 10 to 63, then the plot only changes. The count was not in the model. But when we changed, let's see here, count again. There we go. When I changed the distance from 0 to 2000 to like 288 to 2000, now all of a sudden the plot and the models and everything downstream all get invalidated. Here's our predictions, here's our output of the root mean squared error, the AOC, the table, and then also the plot gets invalidated. So all of that has to get recalculated. So it's really nice to be able to see what Shiny's thinking. And when it would be done calculating, we ended up there. Last few words on Shiny optimization, because we always like to push things to the limits, or at least I like to. Most likely, if you believe your Shiny app is slow, there's lots of things that we can do before we can declare it slow. One, move work outside of your server function. Every time a user joins your Shiny app, the server function is executed. So if you're loading data that is static, such as like original data equals read CSV, put that outside your server function. By doing that, you're pre-processing your data once, not for every time a user arrives. And so that's really useful. Your user load time will drop all of that calculation time. It'll completely remove it because it's just at initialization, not at user initialization. Second one is make your code faster. I like to believe I write good code, but it's not always the case. Run profviz, find out where the slow parts are, remove them. If there's no slow parts, great, you can fix that, but most likely there will be. Sometimes it's just a weird lapply, or it's a weird for loop. You never know. Sometimes they're not the problem. And then last one that I like to use is caching. Also in the new update in Shiny, plot caching was enabled. So we all know ggplot2 is not the fastest. And so we've tried to get around that by saying, well, if you give me a certain key that I can listen to, at least in Shiny world, reactivity, we'll say that the plot is the exact same plot given the same key. And so if the first person comes in and it takes a little bit to load, but it finally finishes, then it has some key of like, position 1. And I come in and say, oh, please give me position 1. It will be instantly returned. And I won't have to wait the 2 seconds that ggplot takes to calculate. Super awesome, especially when lots of people are looking at your application. And then very rarely, I'm talking like 1%, or when you've spent 1,000 hours, use async. But really, you're not going to get too much more. I think the first 3 are like your big signals of where slowness comes in. I haven't really found a situation where async might make it better. Possibly in model calculations to free up resources, but I would say it's not your winner. Most likely it's stuff that you can do on the surface. So The slides are posted, and there is a link completely underneath the slides. It's something just to click later. It's Joe Chang's keynote from our studio conference, and he goes into this in full depth. So if you're in a situation where you're like, okay, I need to worry about deploying this to more than my 5 teammates, like this is now something to listen to. Yeah. Any questions?
Can you describe briefly what that async thing you just mentioned was?
Sure. So R is synchronous, and R is single-threaded, and you just execute, you're done. That's how it works. Shiny works with a runtime in that when a user makes a change, it happens later. Like it's not at the initialization, right? It happens at a later time point. There's even one more situation where you can say, here's a value 5, and in 30 seconds, tell me 5 plus 1. Do some calculations. But in the meantime, allow people to do things in the console. And I think it's really weird in how it works, but that is async for R. And what we do is we just put it into a different thread. Don't need to worry if you don't know about it. Different thread, and then it waits, and then it comes back and takes control of the console. So hopefully I can do this later. Function of low. And I'm going to, oh yeah, let's raise it up there. Print this. And I'm gonna do this 10 seconds later, right? So I do 1, 2, 5, I, and I think about it. Hello. That's really weird, and it works really well if you have a certain particular case. Another situation is if you have a model that is iterative. This is one time where I would say async is good. If you have a model that's iterative, meaning that you're going to calculate 100 steps or optimizations and then you're done, but that optimization period is like 100 seconds of blocking, that means that anyone else trying to use your Shiny application can't do anything because it's blocking for 100 seconds. But if I had to wait 1 second, that's not bad. So what you could do is you could chain 100 promises of async calculation, and so it would return right away. There'd be nothing working, and so it would start calculating on the first iteration, and then it would spawn to the next one, and the next one, and the next one. But if I came along and said, please give me the website, it'll say, oh, let me insert a request in between your async calculations, and it will return for me right away. So I wait at most 1 second, but your calculations can still continue. And maybe that didn't make sense to a lot of people, but if it's needing something, that's one place where promises or later is very, very useful. I just find it crazy.
Any questions? Well, thank you, Vera, for coming to talk to us. Thank you.